Hi, this is Thomas. Welcome back to math class. We're continuing to look at the concept of transformation of nonlinear functions to straight line form. In the first lesson, we learned how to get from the linear form to the underlying function. Now we're going to look at the underlying function and determine how to convert to a linear form or transform to a straight line form. So let's start with the example of y equals 2x squared plus 1, which is an example that we saw in the first lesson. In this case, the relationship isn't y to x, but there is a linear relationship. The linear relationship is between two variables, and they are y and x squared. I don't have a linear relationship between y and x, but I do have a linear relationship between y and x squared. If we think about this function from the standpoint of the slope-intercept format of a line equation, y equals mx plus b. I have two variables in this general form, y and x. And x has a multiple, which is the slope, and there is a constant value, which is the vertical axis intercept, which we usually refer to as the y-axis intercept or y-intercept. And notice that I can match a variable to each of these variable locations in the general form. Instead of y and x, they're y and x squared, but I do see a linear relationship in y equals 2x squared. The relationship which is linear is the relationship between y and not x, but x squared. So that's already in a linear relationship that we can identify. So let's take another example. Y equals 1/2 x to the power of 3 plus 3x. Now this example looks somewhat like the y equals mx plus b format, but in the final term I have a variable, plus 3x. That's not a constant term. So I want to get the final term to become constant. What I need to do is I need to divide by x. So I'm going to divide the entire equation by x, and I'll end up with y over x equals 1/2 x to the power of 3 over x plus 3x over x. And I'll have some cancellations. 3x over x becomes 3. 1/2 x cubed over x becomes x squared. And now my equation is y over x equals 1/2 x squared plus 3. So let's see how this equation fits into the line-intercept equation format of y equals mx plus b. I now have a linear equation. The variables, instead of y, I have y over x, and instead of x, I have x squared. Y over x is one variable that's represented by y in the general form, and x squared is my second variable represented by x in the general form. And I have a value for m, or a slope, of 1/2, and a value for b, or my y-intercept, of positive 3. So now I have the linear relationship that represents the underlying function, y equals 1/2 x to the power of 3 plus 3x. That relationship is linear between y over x and x to the power of 2. Okay, let's look at another example. The function is y equals 1/10 times x to the power of 3. And I'll actually put my second example on the whiteboard now as well, because understanding how these two examples are different is an important distinction that you want to be able to make. The second function, y equals 100 times 10 to the power of 1/3 x. The first function is an example of a power relationship. And the second function is an example of an exponential relationship. When the variable is the base and a constant is the exponent, that's a power relationship. And when the variable is a component of the exponent, that's an exponential relationship. With a power relationship, the linear relationship is between the log of y and the log of x. And we'll use base 10. We could use any base. So knowing that I'm dealing with a power function, a power relationship in the underlying function, I'm expecting the linear relationship to be between the log of y and the log of x. With an exponential relationship, in my transformation, I'll see a linear relationship between the log of y and the variable x. So the significance of this notation is that you want to be able to recognize the first example, the first function example as a power relationship between y and x. The second example as an exponential relationship between y and x, so that you can anticipate what kind of linear relationship you will see when you complete the transformation to straight line form. So in our first example, we expect the two variables in linear form to be the log of y and the log of x. And in the second example, we expect the two variables to be the log of y and x. So the transformation of our first function, I'm going to multiply both sides by 10 to get to 10y equals x to the power of 3. And then I will take the log base 10 of both sides. Log of 10y equals log of x to the power of 3. I can manipulate the right side of the equation to become 3 times the log of x. I can manipulate the left side of the equation to become log 10 plus log of y. Log of 10 is equal to 1 plus log y equals 3 times log x. And I can subtract 1 from both sides to get log y equals 3 log x minus 1. And now I've transformed the function to a linear relationship, looking at the format y equals mx plus b. The equation, the linear equation variable is log of y, which represents y, and log in the second variable is log of x, which represents x. So now I have a linear relationship between two variables, the log of y and the log of x, in the format y equals mx plus b. Now our second example, y equals 100 times x to the power of 1/3 x. This is again an exponential relationship. I'm expecting a linear relationship between the log of y and x. So I want to begin by manipulating the right side of the equation so I can get to a base of 10. I want to express the right side of the equation in base 10 so that I can then convert to a logarithmic equation. 100 is 10 squared times 10 to the power of 1/3 x. This simplifies to 10 to the power of 2 plus 1/3 x. And now I can use log rules to convert from an exponential equation to a logarithmic equation. My base is 10, so I'll use log base 10 for the value of y equals the exponent, which is 2 plus 1/3 x. And finally, I'll rearrange the right side of the equation to log of y equals 1/3 x plus 2. And again, looking at the slope-intercept form of the line equation, y equals mx plus b, I see that my variable log of y is in the place of y, and x is in the place of x. So I've created a linear relationship based on the exponential relationship given between y and x. I've created a linear relationship between log of y and x. So we've seen 4 examples of evaluating nonlinear functions to identify linear relationships. This ends our lesson on transformation to straight line form. Thanks for watching, and I'll see you in the next lesson.